Okay, if no, then we start our lecture. Huh? Okay, record. Okay, Monday the time, okay, we stop here. We say that, okay, if you are using any integer, okay, we must make sure that, okay, we decide on the type of integer that we are using, whether it's a sign or unsigned. All right, just now in the lab here, we are using the unsigned. Huh? All right, okay, so you can only open up this library, either one of them. Okay, so we proceed here. Now, looking at those operator here, in the list, okay, that we looked at it earlier, there is a priority of the list, okay. Say like a simple example here, we have this component or entity, which is a logic, okay, 3 input, 2 output, both are standard logic informations. Now, I am going to look at the architecture here. The Z is the one of the outputs is A and with B. Okay, A and with B, we know is this one. All right, and the Y here is A and with B. So this bracket here tells me that I must do A and B first before I end it. Oh, sorry, before I OR it with my C bar. Not C is the C bar. So with this one here, this bracket here is having higher priority. All right, you can say that if I don't want to put, is it okay? Actually, in terms of syntax, no problem. But in terms of logic, okay, it may be wrong. So this is the reason why I say, okay, comparison, they check your syntax, but not the logic. So you don't put the bracket, they still accept it, no error. But in this case here, okay, they may, don't know, it depends on the system. Maybe they are going to produce you, okay, the circuit looks something like this. They do the one at the back here first. B or we not get first, then they end it with A. Or they may do this one. If do this one, yep, this is what you want. But if they do this, okay, then it is wrong. So we add in this bracket here is to prevent ambiguity. All right, or prevent logical error. All right, so this is important. This is what we call as a logical error. If you don't add in, system may be wrong. All right. Okay, for the case of multiplier, actually we have seen this example before. So you find that in terms of arithmetic operator, I can do multiply. And this multiply features here, this one, make the whole thing here very easy for us. I just multiply. I don't care how you arrange your gates, okay, in terms of structural or what is the VHDL code that you are using. I just multiply my A with my B, and my A in this case here 4-bit. If you do, okay, this design, this one will take very long time. All right, VHDL just solve it for you. You just timestamp, and the result that you are going to have here will be 8 bits. Okay, 7 down to 0. Of course, okay, you say that, okay, I put 4-bit, can or cannot? Can, no problem. But then the result is wrong. Okay, because 4-bit times 4-bit may give you, okay, a maximum of 8 bits. All right, so you have to cater for all these in terms of logically the correct answer. All right, and in this case here, since, okay, this part here I'm dealing with finally the answer, so unsigned. Okay, I declare those number that I'm going to have here is unsigned, means that the magnitude here representing the MSB, MSB here representing a magnitude rather than a sign. Okay. Okay, this one here also looks like we have seen before, but then But then now, okay, look at it, okay, we try to understand what does it mean by concatenate. Concatenate here. Okay, I have this 8-bit adder, and the result here is 9-bit. Why I need a 9-bit result? Remember the carry bit, the C out. Okay, the C out. Okay, so we start off with saying that, okay, this adder here is 8-bit. So both A and B are A and B are 8-bit. So 7 down to 0. My sum here, this sum here S is including your carry out already. And you'll find that this is 9-bit. 8 down to 0. So it's 9-bit. Now, with these parts here, you are going to find that if I take S, okay, I take S, I assign my S, okay, with the value of A, okay, this is an arithmetic operation, A or with B. Now, we know that A is a bit, B also a bit. But now, because the S here is 9-bit, so if I were to write my code as in this form, the system or the compiler will tell me that error. Why? You cannot have, okay, different length. Okay, you cannot have different length. This one 9-bit, you must make sure this is 9-bit. This is also 9-bit. So with this, okay, I have to add in one extra bit to my A as well as my B. How to add? So we put concatenate. So whatever is the A here, now this extra bit that I put in here, I put to the MSB. MSB to the B as well. So I'm changing the A from 8-bit to 9-bit. Same thing here. So that, okay, when come to additions, and come to, okay, compilation, it can be accepted by VHDL. So this concatenate means that you add in, okay, make the length or make the this vector here from 8-bit to become 9-bit. Okay, concatenate. So see this symbol means concatenate, means you add additional bit to it, or you are combining this bit into the A. All right. So remember, when you are doing any additions and so on, make sure the length are the same. So this one cannot, so we convert it into this form. Okay, next we proceed. Now in VHDL, there are a lot of these, features. Okay, the attribute of these codes here. So there are many of them. As okay, representing, okay, whatever the variables, okay, general S. So you can, okay, have left, you have right, the highest number. Left here, okay, you take the leftmost components in the data. Rightmost components in the data set. Okay, the data set in this case here contains more than one info lah. So you want to take the rightmost. This one you want to take the leftmost, or you want to take the highest element, the lowest element, high, low. Okay, okay. You wanted to know the range of the data types. All right, you want to do the reverse, length, event, and stable. Now, all this here, this is the one that we use the most. Event in this case here, when you are changing, okay, from low to high. Wow, my drawing is no good. Low to high, okay, a straight line, okay, low to high, or a high to low. So this is an event. Okay, this is an event. They always, okay, go together in our clock. Okay, say for example, the S now I'm referring to my clock CLK. Okay, I put clock event and I animate final result that I want. Let's say I want the clock to be at logic 1. Indicating that, okay, these conditions here, I'm talking about this part. This is an event. I want it to stop at logic 1. All right, so this way, I'm talking about this part. If the balik, okay, I want the falling edge, then you take the clock here and at logic 0. So with this, okay, event, okay, stop at logic 0. So signal going down. So this is the falling edge. So this is the one that we use the most. But all these info are available lah. So other than this, okay, sometimes we also wanted to signal to be stable. Okay, clock stable at certain value, maybe 0 in this case. So no change value at the current simulation time. I want the clock to be stable at 0 or clock to be stable at 1. Okay, if you are talking about latch, okay, responds to a level. Okay, flip-flop responds to H. It's a H trigger. Okay, flip-flop, okay, when we cover sequential that time, it is a H trigger. I find it getting more difficult to control nowadays. Okay, it's a H trigger. Flip-flop, If it's latch, then it is a level trigger. Level means that, okay, either it's a logic 1, stable at logic 1, or stable at logic 0. So both here you can see a D latch or D flip-flop. Okay, common one is D latch or D flip-flop. So when you find that, okay, they are responding time, okay, they react to level, then you know that you are talking about latch. Okay, if they respond to the H, then it is a flip-flop. Okay, so these are the two, okay, that we commonly use other than the rest all on top. But for this lecture here, I just add in everything. All right, next, okay, we look at a concurrent statement. Now the word concurrent here tells you that, okay, at the same time, they work at the same time. Work at the same time. Sama sekali, masa at the same time here. Now there are these concurrent statement here, which you call it. There are many of them, okay, that can work at the same time. So you have concurrent signal assignment, conditional signal assignment, selected signal assignment, block statement, concurrent asserted statement, and your process statement. Okay, so we look at it one by one. So in this concurrent statement, as I mentioned just now, they will work at the same time or they execute at the same time, all run at the same time. So these are the example, okay, thereby you find out, okay, how these concurrent statement are being applied. Okay, so you are going to find that, okay, signals impacted by an event are resolved in the same simulation time. Everything here is going to change at the same time if you are talking about the same variable. So we look at one by one. My A out, okay, A out is assigned same as A. Don't ask what they are doing, because we are just taking it as just an assignment, okay? No special features that this program is trying to produce. So my YO, for example, okay, I just simply take it as it is assigned as A, you end it with B. Y1 is a 1 when my A is a 1, else 0. That means that when my A is 0 that time, my Y1 is a 0. What I understand by this meaning. All right. Okay, so look these three first. Now, the first one here is a signal assignment. Second one is a Boolean equation, AND gate. All right. Third one is some condition. You are checking the A condition. So they call it as conditional assignment. All right. Fourth one, this is where you see in your structural model. So when you see the word pop mapping, pop map, okay? So it is a component instantiations whereby you are telling that this one connect to your A. This one here, the in A, this is in A, is from your component that you call out or the entity that you store in your database. Now you want to connect it to the A. All right. From your components, okay, of the output, okay, output B, you now try to connect it to the B of this particular entity. Okay, these two here, wow, I should choose the red. These two here are actually, okay, come from the component called out from database. Okay, you now try to sort of, okay, connect it, okay, to whatever existing, okay, your new components. Their output here be a output or input. All right. Okay, so this is component instantiations. Okay, next process. Okay, let's say my list process here depends on clock as well as two inputs. Now process the sensitivity list. This is what we call sensitivity list here. Always, okay, contains only input. Never put output inside here. Only input. So that is to say that all these things here will be running one time if there is a change in the clock in this case, as well as if there's a change in the A signal. Okay, so begin clock event and clock equals logic 1 tells me that my this process here responds to rising edge. So only when this thing here happen, I will then check this. If they check the first line here, no, this is wrong. It is a falling edge now, then they just skip. They will end the if. Okay, they will skip this and end the if and end the process. So if they meet this requirement, then they check, is my A equals to 1? Answer yes. If yes, then you do this. Whatever data in, you assign it to Y. If it's wrong, again, okay, after this, skip this one, and your if, and your this another if, okay, and your process. Okay, why write this those are statement as in this form? Here is trying to you are going to find that, okay, every, okay, statements here I involve A. Okay, here say if an event occurs on A, something happens to A, then all these statements will execute at the same time, all change at the same time. So this is tally to our hardware. If we were to connect in the hardware, okay, all these different components, we connect it to the A input signal. You find that when A change, automatically, okay, all my hardware here will be changing at the same time. So VHDL is not just programs, it's actually trying to mimic all the hardware that we do in the lab or practically. Okay, I repeat here, when A change, all these statements here will be changing at the same time, or I should use the word response at the same time. May not be changing, it depending on the B condition as well, but they are going to respond. Okay, no change, then stay lah. If there is a changes, okay, change accordingly. Okay, so when these things happen, we say that, okay, they are being executed concurrently. Okay, they work concurrently. Okay, this is the one at the same time. Now, in this concurrent signal assignment here, okay, always you can only see in the architecture. Okay, changes on the right hand side, this one, for example, the A, changes on the right hand side will immediately, okay, be seen on the left hand side. Okay, immediately, okay, reassign to the left hand side. It can be used in the behavioral or in the structural descriptions. So all this one here, although we say, okay, happens concurrently, but respond, it takes some time, isn't it? But the time is so fast lah. Okay, the time is so fast. Okay, so if you never assign anything, then the response time is a delta time. So it could be 1 picosecond, it could be 10 picosecond. It depends on how complicated is your circuit or the expressions that you are dealing with. Okay, if you never assign. Okay, So some, okay, want it to be very precise. They will tell that, okay, I want this output here, or give me the correct output only after, let's say, for example, 10 picosecond. Then they use the word after. Okay, so I will only see the result after 10 picosecond, for example. So you schedule the timing. But in most of the time, we don't schedule. We let the hardware, okay, depending on how fast they can respond. All right. If this is the case here, you find that delta time. We are using a delta time. Okay, very short timing. All right. In this type of signal assignment here, the operator that you are using is look something like this. So this one here we read as assign. So this is not less equal. This is assign. All right. So the syntax looks something like this. Okay, the target that you want to assign. All right, you put in the expression, and the one in this bracket here is optional. You can put in after certain timing, or you don't write it at all. So if you don't write it, this is what we refer to as delta time. Okay, you are doing it as a delta time. Okay, next. So you find that, okay, in some cases here, we may have a y, for example, okay. Y value could be a, could be a b. So y, okay, is assigned as a in one of the process, but b in different process. This is where your if statement, or we call it as a multiple driver. This multiple driver, if you still remember, can only work with standard logic. Okay, work in standard logic, not the standard U logic. So this is the reason why we study standard logic only. All right. So to resolve, okay, this type of multiple driver here, you normally use the if statement. Okay. So example here is I begin this, okay, with saying that if something, okay, will decide that whether my y should be a or should be a b. So let's say I just take when s is a 1, very simple example. This one here, if it is a logic 1, this is not integer. If it's a logic 1, remember to put in inverted comma. All right. Then indicating that the S is a logic 1. Then you say that, okay, y I am going to assign as A. A, finish. All right, so semicolon. Else in this case here, indicating that my S, okay, could be a 0. So there's no need to write. Okay, if S is not a 1, then they will all fall into this category called else. Then in this case here, you are going to assign the y here with a b. All right, so I have done this. And remember your and if, okay, you put it same line as your this if here. So you end if. Then if this is in a process, you end your process. So since I didn't write it, I am going to stop here. Okay, so this part here resolve the problem of multiple driver. You decide, okay, get something, okay, the S in this case here to decide for you, should my Y be A or my B. So this is what we call okay, resolution function. So every time whether the driver is going to change value or not depends on my S in this case. All right, okay. Now we look at more details on this conditional signal assignment here. So the conditional signal assignment here may not be just as simple as this one. Okay, it can be more complex. All right. So say for example, this one of the example here, I have my target. Okay, I'm going to assign it as first value with this condition, else different value, then different conditions, else third value. So that to say I check more than one. So with this one here, sometimes it's like that. Okay, this condition here is no vector. So if vector, you put double inverted comma. So first value, if this condition is this one. Oh, second condition, let's say I just simply choose 1, 1. Okay, 0, 0, you got first value. 1, 1, you take the second value. If 0, 1 and 1, 0 that falls into this else, okay, then you are going to take the third value. You can have more if your conditions here got more digits. Okay, so this is only 2. So you can have 3 or 4 or whatsoever. Okay, so a more specific example here is, okay, y is assigned as in 1, okay, input 1, when my s is a 0. Else, y will be assigned as input 2 when my s is a 1. Else, okay, it is a 0 because your s in this case here could be is a standard logic. Remember your standard logic, we have something called don't care. We also have a high impedance. Let's say the input for s now is a high impedance, the z. Then your y will be assigned as logic 0. All right. So y can also be assigned something like this. Okay, y is assigned as, oh, it's a vector, 0, 0, when your count is more or equals to 8. Anything more than 8, my y will be assigned as 0, 0. Okay? Anything more than 8, your y will be assigned as 0. Else means less than 8 lah. All right? Then your y will be assigned as 1, 1. Okay? So your conditional assignment, okay? The conditional signal assignment can be very simple or getting more complex depending, and provided it is logical, okay, then this VHDL can accept it. So this is only few of the example. So when you are writing, okay, your VHDL code here, sometimes you may want to insert that, oh, my program is run until here, no error. Okay, so you may sort of, okay, later on add in under some syntax. Wow, I'm going a bit too fast. I'll talk about it later. So this signal assignment here, okay, we can have concurrent versions of a case statement. I like this one a lot because, okay, it makes my programs, okay, very neat, tidy, and easy to understand. So in this case statement here, there are two ways, okay, of doing it. One is with expressions. So you are going to say that, okay, the output or the target here, you are taking it as expressions when certain choices. Difficult to understand, right? Never mind. We look at an example. So with data in, I select, okay, y as input 0, when 0, 0. This 0, 0 refer to my data in 0, 0. All these are data in. Okay, data in. Okay, y will be in 1 when data in is 0, 1. Y will be in 2 when data in is 1, 0. So in this case here, there is one more that I haven't select, is a 1, 1. Okay, or maybe the ZZ, high impedance. Wow, a lot of combinations. Okay, and da. So all this one here will be classed under the others. Okay, semicolon. All this will be classed under the others. So we put in this, okay, is to safeguard ourselves. Anything not mentioned here will be all categorized in this category, and my output will show me the in 3. Okay, and by this codes here, I also can sort of, okay, see as, okay, I have one components that I try to design. 1, 2, 3, at least 4 input. Okay, the in 0. So this is the in 0, in 1, in 2, in 3. And my output is a y. Whether, okay, this one here, which one will be the output here? It depends on something called your data in. Okay, and my data in this case here is 2 bits. Okay, so maybe I draw it 2 bits, and let's call it as D1 and D0. So you see, okay, with this type of way, I can actually visualize how my entity or how my this device that I design looks like. So this one here, decide which one to be the output by checking the conditions of my theta in. When 0, 0, take this one. When this one, take this one, and so on. This one actually will meet a multiplexer. This is actually a 4-bit multiplexer. Okay, 4 input are 4 to 1. Okay, 4 to 1. Okay, multiplexer. Okay, so you can write your program in this case. And look at here, read is a reserved word. Okay, you select is a reserved word. Then others also reserved word. So this is using read expressions for this part. Okay, so let's say now I have an example whereby I have a tri-state. Tri means it's 3. It's a 3-state buffer. That to say that my output in this case here, beside here 0, 1, I'm going to have a Z, high impedance appear. All right, let's look at these programs here. Library IEEE. I open up this library. All right, entity name, my state is A 4-bit. Okay, so in standard logic vector 4-bit. EN stand for enable. Okay, enable input 1 bit, and my output here 4-bit as well. Okay, and my this my try. So architecture behave of my try is okay. I begin and say that okay, my y is assigned as a. Okay, y is assigned as a with this condition when my enable is a logic 1, else others. These are others here, very powerful. So this is 4-bit, okay? You can say that, okay, you can say that else, okay? 1, 2, 3, 4, because 4-bit, ma. Okay, you can say this way. But imagine that, let's say your y is 32-bit. You are going to type 32 0. And you type, forgotten. Oh, okay, calculate again. Very time consuming, isn't it? So you use these statements here. Don't care what is the length that you are referring to. You can just take it as others all assigned to whatever figures that you want. Okay, so if this is you want to assign as 0, you just take it as 0. You want to assign as high impedance, you just put in the single Z, okay, or a single 0. Okay, rather than type 32Z or 32 in this case. Okay, here trying to say that when enable is a 1, Y will be assigned as A. Else in this case here refer to enable equals to 0, then your Y will be at high impedance. Okay, 4-bit means this one. 32-bit also means, okay, they themselves will know, okay, the length. They just go and fill up, okay, whatever is the output in this case for you. Okay, look at this structure of these programs here. This is a buffer. All right, so I got an input A. A value can be a 0, can be a 1. Okay, because it's a standard logic vector. Okay, can be a 0 or and 1. So whether you want the output here to accept the A or not, controlled by this EN enable. It's something like a gate lah. Okay, when gate open, okay, signal pass. When gate not open, you high impedance means disconnect from other circuits. Okay, disconnect. High impedance disconnect it from other circuit. So you can write your buffer, okay, as in this case. So this part here is important, is this one. Okay, it means in this case here, y I'm going to have that value. Y is 4-bit. If y is 32-bit, same statement I put in, they will come up with 32Z for me. Okay. Now, if I have a truth table, Okay, if I have a truth table as in this case here, well, how am I going to write this truth table here? Okay, so this part here is trying to introduce you to this one here. In the case here, this is the all. Okay, so we look at it one by one. So this is a truth table. Don't ask what is the gate for. Okay, just accept it. And I have, okay, I have to start my list of program here with library IEEE. Use the standard package. Then entity, give it a suitable name. Truth table is, I got ABC, okay, ABC input, okay, and the output, one bit only, okay, out standard logic, and my truth table. And you are going to find that when you are using case statements or the with statement, case we haven't seen, okay, the with statements here, you won't look at them individual bit. You try to combine them together. So when I combine my A with my B, okay, sequence is important. So if I write this way here, my C is my MSB. Okay, this is the LSB. So result coming out of doing concatenations of this case here is actually same as ABC. Let's say now you have the combination of 0, 1, 0. Okay, 0, 1, 0. So automatically they know that, okay, this A is a 0, B 1, C is a 0. So you concatenate them or combine them from, okay, from bit, one bit here to become a vector. Okay, so you find that now in this architecture here, I am going to declare a signal. My list signal here is actually combining the ABC input. Okay, concatenate them or combine them. So now my S1 is ABC, representing ABC. Okay, I concatenate ABC. Okay, with S1 I select. So S1 now conditions I need to analyze. So all in there are, because of 3-bit, all right. So you have 8 different combinations. And all of these are 8 different combinations here. Some combinations here will give you the same output. Okay, 3 of them here, okay, give you the same output, which is a 1. Then another 3 give you 0, 2 more give you the, this is a don't care. Okay, don't care. So we use the with, okay, expression with S1 I select. Okay, Y will be assigned as 1, 1, 2, 3 with this input combination. This one or this one or this one. So then first or 0, second one 0, 1, 0 condition, third 1, 0, 0. So I repeat this part. Y will be assigned as 1 when with S1 equal to 0, 0, 0 or 0, 1, 0 or 1, 0, 0. So this part here, okay, is equivalent to all only in the with or your case statement only. In other cases, okay, if you type this one here, sorry, it is not all. All is a positive logic, okay? Or you write it as all, okay? In expression, it's positive, but you write in BHDL as OR. Only in this case here, you can use this one. Okay, next, my Y will be assigned as 0, okay? Then S1, okay, is 001 or 011 or 101. And the rest, okay, you don't want to further elaborate, okay? You just put it as Y is assigned as don't care terms, then others. That means that S, any other value not listed here. And it's also covered for in case, okay, there is a problems in the system, then you see all the output here become don't care. Then you realize that, okay, my hardware got problems already. All right, so repeat here. So this is more than 1 bit, therefore I use double inverted comma. or in this case here, only in the with statement, I can use this type of straight line. So this one here, if you see in the, okay, it's a straight line here, okay? So with this type of arrangements here, you find that, okay, you can sort of, okay, explain your this Kano maps here. Sorry, truth table here easily. Of course, okay, if you know what is the gate of this one here, we can directly use the gate lah. But in case, okay, some truth table, okay, do not referring to a gate, it is a more complicated one, or maybe 4-bit lah, 8-bit and so on. You can, okay, just use this method to describe the truth table easier. All right. Now another, okay, concurrent statement here is the block statement. So I want to block it. So this is a latch, okay? Latch in the sense that look at the clock here. You don't see this one. Once you don't see this one, that means that they are response to level, either a logic 1 or a logic 0. Okay, so response clock react to logic 1 or 0. Logic 1 or logic 0. So logic, okay, always, okay, we put in this inverted comma. So if this is the case here, this is a latch. So D latch. And this D latch here will only work, okay, when my clock is a 1. So we can use the block. Okay, and this one here refer to a name of these blocks here. Sukahati, any name, okay, as you like, but with some meaning. All right, so let's here we block it, okay, that's to say that when clock is a logic 1, all these things here will be executed one time. Okay, so if you have a name for this block here, this name here, when you end this block, you must also put in this name, same name. Okay, so reason why here is, okay, in this architecture, sometimes we have more than one process or one block. So to avoid ambiguity, we name them accordingly. Okay, so when you are using the block here, that means you gathered the inputs. So Q, my output, okay, is whatever the changes, okay, at the D here will all go to the Q, will be assigned to the Q when clock is at logic 1. So they use the word here, gathered D. Okay, D in this case here is my input, gathered. So block with gathered. All right, so this is the all the concurrent statements. When something happens, okay, you find that, okay, they will run one shot. All right, you can add in, okay, your own statements. Like I earlier mentioned a bit that let's say my program is very long, okay, and I'm afraid that, okay, I make mistake in the coding. So what I do is certain part of the programs here, I insert, okay, some conditions to confirm that, okay, they really work or run until this part here. So if this is the case here, I want the programs to give me a report. Okay, report a diagnostic message. Okay, until that part already show me a report. So what you can do is you assert the conditions. Okay, so you add it in on your own. Report whatever you want to see here. Okay, and indicate, okay, severity in the sense that maybe you are the programmer, you wrote this program already, but you are not the user. So user see this one, oh, warning, never mind lah. Error, I must solve this error, things like that. Okay, that we see this morning. I told you, warning, forget about it. Different version, okay, they have different numbers of warning. So it's just to alert only, so no mistake. All right, so here you put in certain condition and you want the systems here to report to you, okay, the messages, okay, when these conditions are met. Okay, so this one here is for programmer or for user to see and understand. But come to synthesis or doing compilation that time, they won't show you error. So in the case of synthesis, well, this is accepted because it will be straight away ignored by the sensitizations. Okay, next we proceed. Okay, now we look at this process statement. Now, process statement is particularly useful when you want it to run every time when there is a changes. Okay, so inside this process statement, you are going to find that there is a set of sequential statement. That means that things are going one by one. But in the process statement, everything happens, okay, within the same clock pulse. So when I see the output, okay, I'll say, oh, all work at the same time. But you know, nothing is working at the same time inside this process statement here. They still process one by one, okay? But they show you the result after they already process everything. So when you see the time yellow, they are working it all at the same time. Okay, all processes in the design execute concurrently. Processes. You have many process, all process, okay, if respond to the same variable, they are going to work at the same time. But at any given time, okay, only one, this is what I mentioned, they run one by one, only one sequential statements are executed, okay, within every process. So I will sort of, okay, talk about this one a bit later. So next, okay, this type of processing here, you find that, okay, they can be communicates with the rest of the design through the signal. So syntax looks very, okay, very complex here. Now, for all the process, Sukahati, you can give a name or a label, up to you, optional. Sensitivity, also optional. But if you, okay, didn't put in the correct sensitivity, so you are going to find that logically it is wrong. All right, you can test out, okay, when you are doing assignment. Without this sensitivity here, okay, they just don't run, okay? So if put in too many also, okay, it's a waste of time. So we choose the proper input signal to be placed in this sensitivity list here. Then inside here, I may want to have some signal, things like that. Then only I begin and give you the sequential statement. Now process will be called concurrently, but this one here run one at a time. Okay, run one at a time. So we call it as a sequential statement. Okay, so if this process here you have a label, make sure you end it, okay, the process, okay, with the label as well. Okay, so we look at it, okay, in a more further part, okay, sequential, like no end here, so they call it as pseudo infinite loop. So when you are responding to some sensitivity input element, this one will run and output you the value. So whether I'm going to put in the sensitivity list or not, depending whether I'm using the if statement or wait statement. All right, so we see at the bottom here. Now look at this one here. I didn't use the word here with no with inside here. So my label for this process, I call it as a PQR. This process here is sensitive to ABC. Okay, A change do something, B change also must do, C change also must do. Any one of these changes, this program got to run one time. How do they run it? Run this one first, followed by this one, followed by this one, followed by this one. So sequential, one after the other. So we call it sequential. Statements executed sequentially, one by one. All right, then end this process if no more changes comes in. Once change comes in, repeat. Okay, change comes in, repeat. So we call it as a pseudo infinite loop. Hmm? Non-stop. Okay, if there is a change in the sensitivity input here. Okay, so in this example here, begin my x is assigned as A and B because this is not a complete program. So just take it as now my A x here is A and with B. Now, next, if my B is a logic 1, then you take Y is A, X, or C. Else, my Y will be A, X, nor C. Either one. Okay? So B is a 1, do this. B is a 0, you do this one. Add this. And at this case here, when A change, okay, my X will be affected. My Y, okay, will not be affected because B never change. But they will run it also. Okay, because if A here changing, causing your Y here to change. A can be a 0 or 1, they NOR it, X OR it, or X NOR it with C, okay, it's going to produce you different output of Y. Okay, so it will be changed. So although my B is not changing, let's say I say A change only, but B is not changing, but this one here got to test 1, test 2, test 3, test 4. They will be running sequentially. So my Y output will also be affected in this case. And the response in this case here will immediately be shown in the Y output. Okay, so this is something with your sensitivity list. Next, you'll find these statements here. How come my sensitivity list missing? This is because I say wait. Okay, I wait until I see a rising edge. Then only I do. If there's no rising edge, I don't do any of this. So if you have a wait statement, then your sensitivity list here you can ignore. So you are waiting for rising edge to happen. In this case here, your clock, rising edge clock. So you can write your rising edge as in this form or CLK. They use the word CLK, follow clock event. Okay. And your clock equals to logic 1. So this whole thing here is exactly the same as this part. Same, okay? So either you do it this way or you write it in this form. They both means the rising edge. Okay, so you do nothing, you just sit down there and wait for this program. Just sit down there and wait until okay you see a rising edge. Then only you start to run this one sequentially. Check whether my B is it a 1. If yes, XOR. If no, straight away jump to the else. You XOR with the C, and you end your if. So you see every time programs are in line, you end it with if. And end the process, okay, with a label if you have a label for it. Okay, so understand the difference whether my process here having a sensitivity list or without a sensitivity list. Which one is better? Actually, well, they are the same, but you are going to find that when come to simulations, if I'm using the wait statements, so my this response time seems to be slower. All right, you can test out on your own. Okay. Okay, sequential statements in the processes. That means those these are things these are of information. Where is my these are the sequential statement inside the processes. So you are going to find that okay, you can have a wait statement if you want to. But remember, if you are using wait statement, no sensitivity list is required. If you put in sensitivity list, then comparison that time got error. Okay, so inside this sequential statement, here you can use signal variables, and very frequent also you use the if then else statement. Okay, we are going to do some this looping the process. Okay, continuous to loop, and the case statement which we haven't seen. All right, and of course any others. You can have a direct assignment. Your A is assigned as say B plus C. These are things. So any other advanced assignment. But normally, okay, very frequent, you are going to see your if then else statements appear in the sequential statement. Okay. So my if then else statements here can be very simple. Just one. Okay. Can have two, can have more than. It depends on this condition that you are referring to. If it's single bit, okay, if zero, then this. I if zero, okay, do this and if. So conditions here getting more complex can be is 2 bit, for example, or more than 2 bits. Okay, so if you have only just like that, okay, you find that okay, this one here without an else, but this one here, let's say more, I need an else statement. If not this one, then this one else. Okay, if this condition correct, yeah. If it's wrong, choose other conditions. Okay, you have if else. Okay, if you have more than, okay, theoretically, okay, you will say that okay, it's a else if, right? But in VHDL, they try to cut short. They use else if. So if you have more than, okay, more than, okay, one optional options to choose, then you may need to put else if. Don't have too many if so just else if this condition is 0, for example, then I do this. Else if, okay, condition here change to 0, 1, for example, I do this one. Okay. Else if, okay, if it's 1, 0, you do this one. So they choose one by one, or they test one by one until the last one you see the else. Okay, the last one, whatever not listed here will be falling into this category of else. Then you do this. And in this case here, because I use only one if only, so I end if. Okay, this one I need to end. Okay, so this condition here is, I repeat, tested one by one. Okay, so you don't put in too many if. Okay, so you use the else if conditions. Okay, it means else if, but combine become else if. Okay, in any of these if conditions here, only one else is allowed, but you can have many else if. Okay, so look at this example here. I have this library. IEEE is a multiplexer. Depends on how I write, and then the VHDL will sort of arrange the component for me one by one. Okay, so it's a type of entity. Actually, it's a multiplexer, but I'm using the concept of if statements to produce it. Okay, entity if mark is for input C D E F in standard logic, and my selector 2 bit. Okay, so in standard logic vector 2 bits. Output multiplexer so only 1 bit. Okay, and my these are multiplexer here. Okay, the name of it. Next, architecture behave of if mark is begin always. Okay, architecture begin, process begin. Okay, anything with the word begin, you have to end it. Okay, end it process. This architecture, okay, name behave, so you end behave. Begin for this, sorry, begin for this process, so you end this process. If there's a label, you add in the label. If no label, end process will do. Okay, for this part here, I got if my S is a 0, 0, then my P out will be assigned as C. P out assigned as C when my S is a 0, 0. Else if my PS is my S is a 0, 1, then I am going to assign the D. D being assigned here. Okay, D will be assigned here if S is a 0, 1. Okay, else if S is a 1, 0, then you are going to output the E, to this part. Okay, else my P out will be F finally. Okay, all the 4 input has been selected. So if you are writing it this way, you are actually producing 3 2 to 1, 2 to 1 multiplexer. Okay, looks like a little bit complex. Okay, 2 to 1 multiplexer, 3 of them. If you are writing your program this way, in the VHDL, they visualize it as in this form. Okay, if I'm using the if then else statements. Whether good or no good, depending. All right. So actually, these programs here may be a little bit long and then a little bit more difficult to visualize these conditions here. So there is one more that case statement which I told you that just now will cause my program here to be very easy to understand, and very neat, when I present my coding. So let's look at this case statement here. I have a case, selector, still multiplexer. So I am going to write as when certain value I'm going to assign. This is one of the simplest one. Or it can be when more than one value. Remember, this is the same as my or with this value or this value or this value. Or I'm going to do some assignment or a range of values here from value 1 to value 2. I am going to have this assignment. Finally, we add in the when others, trying to lump everything which is not mentioned in our this when condition. We all lump it into here. Any condition not stated earlier will be lumped all under the when others. Then you have this particular expressions. Then only you end the case. Okay, so in this case here, this is the syntax. Any one of it you can use it. But let's say we go for the simplest one here. When value, look at this 4 to 1 multiplexer. Now, because this is a combinational circuit, combinational circuit, and any of these changes in multiplexers here will cause my output here to change. Therefore, when come to process the sensitivity list, you're going to find that a bit more. All the inputs, including your selector input. All inputs. And refer this to the top. C, D, E, F are the input of your this case multiplexer here. My S, is a 2-bit. Why must have 2-bit? Because you have 4 input 2 to this one, the number of the input here will, decided by S. S is a square, so causing you, that I got 4 input. You want to have 8 input, then 3-bit lah. 2 down to 0. All multiplexer, 1 bit output. So I define the interface already. 4 input, of my this multiplexer here with 2 bit of 2 bit of selector, 1 bit of output. So in this case here, I try to describe it using the case statement. And you find that it's easy to understand. So architecture begin, process begin, case as is. So for the case, you cannot put in a very complex expressions over here, just one only. So if you have let's say 2-bit separate you concatenate them to form one variable. All right. So case S is when 00, referring to my S is 00. You are going to force your marks out, the outputs here, to be assigned by C. Okay, C is 00. All right. So very clear that, okay, when my S is 00, my marks out is the same as C. Okay, this way. When S is 00, force marks out to be assigned by C. Next, when S, VAS, when S is 01, force marks out to be assigned as D input. And subsequently. Last one, whatever is not mentioned here, actually one lah. And any other, okay, like those high impedance, don't care conditions, you are going to force your marks out here to be assigned by F. Case, you need to end. You end the case. Okay, end the process and the architecture. So by, okay, writing your this mark, okay, in these conditions here, you are finding that, okay, you are generating a 4-to-1 multiplexer as in this sequence, compared to just now whereby you are generating 2-to-1 multiplexer and more difficult to understand. Okay, so this one here straight away. So case statement is very useful in this, and it is exactly the same as the hardware that we are seeing. Okay. Okay, so one more slide, okay, before we end for today. Okay, this case example, for example, this one here. Okay, it's a bidirectional buffer. I got A, E again is an enable, Y is the output, and you find that this one here, Y is the output for this case. Y is also, okay, forms the input to the case of B. So Y in this case here is assigned as in out. Okay, we don't do simulation, no problems. Okay, so now I have A and E, A and E as input. There's a call from lab. Okay, so A and E as input, Y is my in out, B is the output. Okay, now how am I going to use my case statement to perform this? So I know that, okay, in this case here, my process, I can only put in input. Don't put in the output, especially the Y in this case here. You might put in the Y here. No, just the input A and E. All right. In most of the this combinational circuit, all input will be listed in the sensitivity list, because combinational is they react immediately when there is a change in the input. Okay, so my architecture here, I repeat, architecture begin, process begin. Okay, so when you write the time, you don't miss out. Okay, architecture begin, process begin. So my case here, I am going to take E as my control. Okay, when my E is a 1, I'm forcing my Y to take A. E is a 1, my Y will be same as A. When my E is a 0, I'm forcing my Y to be high impedance. Z is a high impedance. Okay, no need to define because this is a standard, okay, under your standard logic. So when others, so E can be in the form of, okay, don't care condition, this and that, then you are going to take Y being assigned as X. My question here, what is X? All right, then you end the case, end the process, and now B, whatever is the conditions of the B, okay, that you want to know, you assign it to the assign from the Y. So B is assigned as Y. So you do this part later after the process. Stabilize ready, then assign to the B and your behave. Okay, so this is what I plan to stop before New Year. Okay, because otherwise, okay, I left with one slide here or one or two slides here. Okay, so now question is, what is X? Anyone can answer me? Okay, X in this case here is not don't care. It's not don't care. So in VHDL, okay, X, okay, they have their own special meaning. Okay, so this X here is unknown. Okay, especially when you are dealing with hardware at that time, okay, they are not so perfect as a 0 or 1. So this X here, if these two conditions not met and your Y, okay, give you an unknown value, it could be a very weak 0, very weak 1. Okay, so they class it as unknown value. So with that, okay, you will know that, okay, maybe my hardware design here got a little bit of problems already. Okay, so I stop my presentation over here. Now, any part which you think is not clear and wanted to find out? Okay, one person missing. That is Adin. Adin missing already. Okay. Okay, Len Jian, okay. The rest, what about the rest? Okay, now after New Year, we continue with this the delay model. So meanwhile, during New Year, the time, please okay do your tutorial, the tutorial 2 and 3. Okay, you can try this 4 also. Is writing the programs. Okay, start to learn, and you can type your programs in the quarters. Let the quarters okay check the syntax error for you. All right. Okay. Any question before we end for today? Okay, no question. I think you're New Year mood already. Okay. So Happy New Year. See you again. Okay, on week 4, Monday. Week 4, Monday. So nobody should be absent. So happy New Year to all. And John,